In a rectangular waveguide, we were discussing about the power transmitted. Okay, so similar to the transmitted power, we have to consider another point here, that is the power loss. Okay, so let's quickly look at that and we can move ahead to the problem. Okay, so power loss. Okay, so normally uh, there is a what you call as the cutoff frequency, right? So if you remember the concept of cutoff frequency, right? Beyond the cutoff frequency, right? There will be no propagation, correct? So there the value of whatever propagation constant, right? If at all we are considering the value of f, so I'll write and I'll simultaneously let me explain. Okay, so if f is less than fc, right? Under this case, right, the propagation constant, right, gamma equal to only alpha, right? So it means the phase constant beta, right, becomes imaginary, right, just implying the wave attenuation. So we know that the beta, this under this condition, the value of beta can be calculated. It is imaginary, so j 2 pi divided by the lambda g, right, where we know that the lambda g value guided wavelength is actually the normal wavelength at which it propagates divided by the cos theta. This is one of the equation we are taking from the basics of wave propagation. Okay, this can be actually written as lambda divided by okay, I'll use another equation for this. Okay, I can write in this way, lambda divided by, if you want to use lambda, this is 1 minus f by fc the whole square. Okay, so that's one way of representing this. All right, now let's see what is the value of cutoff, right? So this implies the cutoff value of attenuation, in the sense the value of attenuation at lambda c, right? That is equal to alpha can be calculated as uh, this is a standard equation which we use. Okay, that normally we have a derivation is there, but since that derivation is pretty much longer, I don't think that will be included in this particular concept. Okay, so I'll directly give it the equation, right? You just verify whether they have done a pretty long derivation to for this equation or not. All right, if it is not there, then no problem. Okay, so that is 54.6 divided by lambda c times root of 1 minus f by fc the whole square, right? This is okay, so many decibels per it's the per length of that particular waveguide. Okay, so that's uh, one equation which we will be using, right, if required in the problems. Okay, so that's one equation, and the alpha, right, because of the attenuation constant, because of imperfect dielectric material, right, that is another equation. If the imperfect, if the imperfect dielectric material is used, okay, used, then we call it as a alpha, that is the attenuation constant because of the dielectric, right? This is the attenuation that is going to happen if you use a uh, improper dielectric, right? The dielectric property is not so good. So in that case also we have another derivation to prove this, that is 27.3 times the root of epsilon r into tan delta whole divided by the lambda naught into root of 1 minus fc divided by f whole square. Okay, again, this is measured in decibels per unit length of that particular waveguide. Okay, all right. So here the delta, whatever delta we use here, right? So this is actually called as the loss tangent. I think you have heard the word, right? That's a loss tangent that normally will be given to us and we'll be substituting that. Okay, so I'll write the tan delta is the loss tangent, right? Again, this concept has been described in pretty much detail when we were looking at the electromagnetic waves. All right, from there we can directly take it and we can substitute. Okay, now uh, actually there are multiple equations we can write for this loss depending upon which mode, right? According to each mode this changes, but since we are not discussing about any specific mode such as T10, T01, T11, TM01, etc., depending on that it will change. Okay, it's not the same for everything. So I don't think up to that level, that depth we need to cover under our syllabus. Okay, whatever we are discussing, right? So just see when you get a question, right? Maybe you can verify your old paper if they are specifically asking for a alpha or alpha d for a specific wave, right? Okay, calculate it for T11, TM11, etc. If that is the case, then we need to go a little bit in depth. Okay, so please verify that once on your from your side and tell. Okay, so we'll be able to cover that if required. But I don't think as of now immediately we have to cover, right, those topics. All right, is it fine? Okay, right, let's go ahead and let's try to solve problems. Okay, right, this is the question. When the dominant mode is is propagated in an air filled rectangular waveguide. Okay, uh, we'll say the guided wavelength. The guided wavelength for frequency of 9000 megahertz is 4 centimeters. Calculate the length A, length B, breadth of the waveguide. So this is the question. All right. So we need to find out A and B. That's all. Right. So just they're mentioning that it's a rectangular waveguide and a dominant mode is propagating. All right. So, so let's try to analyze what is given. So, are you able to recall which is the dominant mode in the rectangular waveguide? Dominant mode of a rectangular waveguide. Yes. Right, because the question is, because no, most of the time the solution is will be pretty simple. Okay, so that's why they, if the direct question is given, everybody will answer, and for that reason, try to they people try to make it difficult by not giving the complete details. Those who are able to recall, yes, they will be able to solve it. Okay, so that's the reason why you can see here, unless and until we know which is the dominant mode of the waveguide which we are considering, right? So we will not be able to write that. So that's the reason. Right? So yes, for a rectangular waveguide, right? TE10 is the case, right? So TE10 is the dominant mode. Okay, that's fine. So when I try to write TE10's what you call cutoff, okay, let me try to write the cutoff, right? Generally, the lambda cutoff of m comma n is given by 2ab divided by under root m square b square plus n square a square, isn't it? Now you see it is 10, so n becomes equal to 0, right? So let me try to write the cutoff for 10 mode, right? So that is 2ab divided by, this is simply m into b, isn't it? M is equal to, sorry, m is 1, so I don't have to write it. I'll just use that part, right? M is equal to 1. It's just b, right? So we'll write it as a b. So that cancels to be 2a. So you see, I can actually calculate the a directly if I'm able to calculate the lambda c value. Correct? Okay, so let's proceed further. So I don't know, I don't have a direct equation to calculate this lambda c, right? But I know that lambda g is given, right, in the question. I can try to relate lambda g to lambda c. That is the lambda divided by root of 1 minus lambda by lambda c whole square. Now you see I'm able to relate lambda g and lambda c. Okay, and you see they have mentioned that frequency is equal to how much? F is equal to, I think, 9,000 megahertz. Okay, so 9,000 into 10 to the 6, right? So let us first calculate the F is given. So let's find out a lambda. C by F. Okay, so C is 3 into 10 to the 8 divided by, this is 9 into 10 to the 9. 9,000 into 10 to the 6. Okay, so get me a value for lambda. Okay, okay. Right, so I'll write the direct without making any modification. How much you get? 0.03. 0.0333 meters. Is it right? Okay. Right, so I got a lambda value. Now let me try to relate. On the left hand side, the lambda g is given in the equation, in the question itself, correct? So you can see the guided wavelength at a frequency of 9 into 10 to the 9 megahertz, 9 to 9 to 10 to the 9 hertz is 4 centimeter, right? So let us equate. So 4 centimeter, right? Lambda is equal to 4 centi, 4 into 10 to the minus 2 is equal to, right? So this lambda value is just now calculated as 0.0333, correct? Divided by under root 1 minus So the same number, I'll write a bracket. So 0.0333 divided by a value lambda c, the whole square. Okay, so this is one equation and only one unknown we have, right? So we'll be able to calculate that. Okay, so find out the value of lambda c by solving this equation. First you solve that, right? Then we'll. So we get 0.001. So it's in meters, correct? Okay, right. So we got a lambda c, right? Once you have a lambda c, let's calculate the value of a. Therefore, a is equal to, right? It's lambda c is 2a, right? So a equal to lambda c by 2. How much? So that is 0.0601 divided by 0.03, right? Meters. So this looks like a 3 centimeter. Okay, that's the required answer, right? Okay. So 0 to a is asked. We can calculate. Then fine. Let's go to another question. Mm, okay. Right. Very similar question, but ultimate values to calculate are different. Okay. So uh, in TE10, the cutoff wavelength, cutoff wavelength, oh no, cutoff wavelength is a question, sorry. I have to find this first. In the TE10 mode, I can just, okay, let's say find the value. Okay, in TE10, find the lambda c, okay, of a rectangular waveguide of length equal to 10 centimeter, with frequency of propagation is 2.5 gigahertz. Right, calculate. Also calculate the guided wavelength. All right, then the group velocity and the phase velocity. So this is the question. All right, so the first part of the question is T10 is propagating. So I should be able to remember that the lambda c is directly you can calculate, right? That is equal to 2a, just like the previous case, right? If I don't remember, I have to write the general equation, then substitute, okay? Substitute m and n value accordingly. So here T10 is given, so I should be able to recall that, okay, lambda c is 2a. So this is equal to 2. A is given 10 centimeters. So 10 into 10 to the minus 2. Right? So yes, you get, yeah, you can directly write 20 centimeter, 20 into 10 to the minus 2. So in the next part, I think I should be able to get the lambda g directly. Okay, lambda g means I can actually directly write it, correct? So I think the lambda is given because f is given, right? Okay, so let me calculate. F is given. Yeah, definitely. Any equation will work. Okay, so that's also fine, right? Yeah, please proceed and tell me the value. Okay, what you get. So which equation you want to use? 1 by, I'll write the same equation, right? Okay, okay. 1 by lambda square should be equal to 1 by lambda g square plus 1 by lambda c square, right? Sure, right? Lambda c is known. Lambda g we need to calculate. Lambda is can be directly calculated from the given f, right? Okay, so just tell me what is the c lambda we are getting. Lambda is equal to c by f, right? So c is 3 into 10 to the 8 divided by f is equal to, right, 2.5 into 10 to the 9. Okay, so first tell me the value of the lambda. Yes. C by f. Okay, so this is 0.12 meters. Okay, we already have the this equation, so I can write 1 by 0.12 square is equal to 1 divided by the lambda g. Sorry, lambda g is what we are calculating, correct? Okay, so 1 by lambda g square plus 1 divided by this is 0.20 square, isn't it? Yes. Okay, so using that, calculate the lambda g. What's the phase velocity? Vp equal to 2 into 10 to the 9. This is meter per second, isn't it? Okay. Now, once you have the Vp, how do you convert it into Vg, the group velocity? It's a pretty standard equation, right? Everywhere, irrespective of which concept we are discussing, okay, this equation remains same, right? The equation is Vg into Vp equal to c square. So this would be c square by Vp. So 3 into 10 to the 8 square divided by 2 into 10 to the 9. Okay. Meters per second. Okay. Next question. So this is straightforward, right? Do you have any doubt? Consider a 2.5 centimeter into 1 centimeter waveguide operated at 8.6 gigahertz. Find part of the question, possible modes. Part B of the question, cut off This is part C of the question. The guide wavelength. All right. So here we need to understand that they are not mentioning about which particular mode we should consider, right? That first thing is that that has not been mentioned. Okay, as we don't have any idea about that, we should be. It is expected that we should consider both of them, right? So let's say we consider in the first case, right, the TE wave. Let's say that TE propagates, right? So that means yes, we need to check all the modes first. Okay, so let's calculate what is the lambda. So lambda is equal to C by F. So that is 3 into 10 to the 8 divided by F is equal to 8.6. Okay, 0.035. Mm, yeah, sorry, that's right. 0.035 meters, correct? Right. Now the condition is that if you want a wave to propagate, right? So I'll just write condition for propagation is that whichever lambda you find, right? That lambda should be lesser than the lambda c. Okay. In the sense I find a lambda of irrespective of which mode it is. All right. So irrespective of the mode, right? The propagation should be lesser than lambda c is what I need to find. Okay, now you see 8.6 is fixed, so lambda is fixed. I just need to calculate the lambda c values of all the modes which I want to check. Okay, so first check TE01, right? 00 does not exist, so let's calculate TE01. What is the equation for lambda c? It is right, T01 is I think 2b, correct? Just you can even solve the same equation we wrote. General equation I'll write here. Lambda c for m comma n will be 2ab divided by under root. First is m, this is m square b square n square a square. So now I think n is 1. So right, first term in the denominator will not be there. Second term is a perfect square. So you have n into a, correct? N is 1. So a cancels 2b. 2b. Okay. So let's calculate. So 2b, this is equal to 2 into, this is 1, right? 1 into 10 to the minus 2, right? Or this is 0.02, I guess. So I see that this is the opposite condition, right? This lambda c is actually lesser than the given lambda. Given lambda is 0.035, but this is 0.02, right? This means TE01 cannot, yes, cannot propagate in this particular waveguide. Okay, I hope the step is clear. Right, now let's move ahead. In the you will consider 10. So this says that lambda c should be 2a, right? Same equation, I make the modifications. M is equal to 1, n equal to 0. Hmm. Yes, now you tell me what happens. Hmm. So 2 into, let me just check just a second. I think A is 2.5 or something. Yeah, 2.5 centimeters, right? Correct. So 2 into 2 point, right? So yes, I can say that this is 5 centimeter, right? This is greater than the given lambda, right? So, right, TE10 exists in this particular case, right? So definitely we can calculate the next value, right? So what was a, I think, okay, let's consider lambda c. So we'll say that what will be the TE11. Okay, find the lambda c for me. But now we need to substitute every value to get this. Correct? So that is 2. A is 2.5 into 10 to the minus 2. B is 1 into 10 to the minus 2, all divided by, in the denominator, under square root. M is 1, N is 1. So simply it is B square plus E. Correct, correct. So 1 into 10 to the minus 2 square. Okay. So this lambda c is equal to 0.018, is it? Okay. 0.018 meters. Now I can say that, is it, I think this is lesser, right? This is lesser than the, uh, oh, okay. So lesser than the lambda. Mistake. So this is lambda. So that means TE11 doesn't exist. Correct. Okay. Okay. So we have, okay, I think if you remember, the modes which propagate, right, can be found. This is what we are solving only for the TE, correct? Right. So we need to find the similar concept for TM as well, correct? Okay. So now, so what's the equation for lambda c in case of the TM? Do you know the difference? What's the equation for lambda c of m comma n? There is no difference. Okay, so same thing. Just I'll write m square b square plus n square e square. So that means, right, all the values will remain same, right? According to this tm, which one will propagate, right? Yeah. So 0 1 will propagate. No, TM01 and TM11, right? Right? Yes. They do not exist, and the TM10 exists. So what's required? I need to calculate only which one, the one which propagates, right? Right? Only the mode which propagates, you need to calculate the cutoff, correct? Because the question says find the cutoff frequencies. Okay, so I'll write therefore. This is the second half question. Cut off frequency. QEN cutoff frequencies. Let's calculate, right? So how do you calculate the cutoff frequencies? Right? It is FC is equal to normal equation. Okay, so velocity divided by lambda c. That's all. Okay, so first we are trying to write TE. I think 0 1 does not exist, right? I think I can write T 0 1 does not exist. 1 0 I can calculate, correct? So TE10, or this is also true for TM10, correct? So what is the cutoff frequency? It is C, 3 into 10 to the 8 divided by, what was the lambda C we got? I think that's 5 centi. So I can write 5 into 10 to the minus 2. Okay, 6 into 10 to the 9. Yes, 6 gigahertz. Similarly, calculate TE11 or TM11. Sorry, 1 1 does not exist. Only 1 0 was existing, isn't it? Correct, correct. Sorry. Okay, so two questions we answered. There is a third question, right? So that says, what's the question? Okay, lambda g, right? Part C answer. So lambda is given, lambda c is also given. Yes, so only for the one which we know we can calculate, correct? So the one which propagates is T10, right? And okay, do you know what's the lambda value here? Lambda, given lambda. Okay, let me just think. Initially 0.035. Okay, okay, correct. The same old equation, you want to use the same thing, right? 1 by, so this is 0.0, okay, approximated to next, okay, 0.05 meters, correct? Fine. Okay, one more similar question for you to solve. That is, if A is equal to 4 centimeter, B is equal to 3 centimeters, operated at 5,000 megahertz. Okay, uh, check whether TE10 and TE01 exists. Also check whether TM11 exists. Right? Two parts we have. A is that, B is this. Okay, please solve.